Welcome to solverfy.
Okay, this is a pretty tricky one. So we have a object with a mass of 20 grams, a vertical distance of 2.5 meters from the ground. It's being dropped onto some small target, and we were asked using quantum principles to find the minimum possible uncertainty in its x location. So we should really draw a coordinate system. In the y direction, we're 2.5 meters off the ground, and we're going to have some uncertainty, delta x, as we fall, some final uncertainty and some initial uncertainty in the horizontal component, delta xi. And we were asked to find what delta x initial would have a resulting minimum delta x final in this free fall. So we're doing a minimization, essentially. So the equations we'll need, we will pull the time for free fall from just basic kinematics. We're going to use the fact that we're going to use another kinematic equation, except we're going to express it in a slightly different way, that the uncertainty in the final position is equal to uncertainty in the initial plus uncertainty in velocity times t. And we'll use the uncertainty principle, delta x, delta v is at a minimum h bar, where h bar is the reduced Planck constant. So let's jump into this. It's this kind of a subtly difficult problem. So to start, we can, using this kinematic equation, that the uncertainty in final position is uncertainty in initial position plus uncertainty in velocity in the x direction times t. We can then express uncertainty in velocity as uncertainty in momentum over mass, which gets us a little bit closer to being able to use an uncertainty principle. So that's actually delta px over m times rt. So now we have a free fall time, which we are going to be plugging in eventually. Let's actually leave it. We don't actually need it for anything yet. But what we will need is the uncertainty principle. We know that delta x is delta x times delta p, the product of the two is h bar. So then we can actually find delta px as h bar over delta x. We can plug that in to our kinematic equation to have delta x initial plus h bar t over m delta xi. Okay. So by doing this manipulation and applying the uncertainty principle, we were able to get our final uncertainty, delta xf, as a function of only delta xi, and the free fall time, which is predetermined. We can calculate it at any time using the quantities we already have. So this is a function that we can minimize. So we can find a delta xi that will minimize delta xf, and that's going to be the objective. So in typical minimization fashion, we are going to take a derivative and find where that derivative is 0. So we're going to be minimizing xf. So we take a derivative of it in terms of xi, delta xi, which is going to be equal to 0 to find these critical points. So taking a derivative of the first term, it's going to simply give us a 1. And a derivative of the second term, so doing just a basic power rule, we have h bar t over m delta xi to the negative 2. So we have an equation for xi that we can solve. We'll do that. We find that delta xi is equal to square root of h bar t over m. So this is apparently the location of for our minimization. So this is the amount of uncertainty in initial position that you would actually want to produce a corresponding minimum value in the final, in uncertainty in the final position. So what is that value? We can now plug in our delta xi into the xf formula. We end up with root h bar t over m plus h bar t over m multiplied by, we got to be super careful about how we do this, square root of m over h bar t. And you see that this is going to result in root h bar t over m plus h bar t over m. Which gives us two of them. So we have 2 root h bar t over m. And that's the main result. So let's get a number for that. So taking a square root, 1.055 10 to the negative 34 for the Planck constant. Our time ends up being 2.26 seconds. And finally, we have the mass of 20 grams. 20 grams is, okay. So my result, after plugging these numbers in, is 2.18 times 10 to the negative 16 meters. So you want a very small uncertainty in your initial x, or this would be the minimum possible uncertainty you could achieve once it hits the ground. Due to quantum, due to the uncertainty principle, of course, it's a little strange that we're doing this for a clearly macroscopic object that's falling a macroscopic distance, but I won't complain about that. These are the main results. We use the uncertainty principle in kinematics and then use some optimization techniques to find a minimum possible uncertainty. And that's it. Thank you.